Week 12, Part 7, Concave Mirrors. So here's a picture of a mirror that's got a concave surface, and I'm showing the optical axis of the mirror and then a single ray that comes in here. We characterize mirrors in a couple of different ways. We usually talk about the center of curvature and then a radius of curvature, which is just this radius line here. I'm going to the center point, this vertex of the mirror right here. That's where I measure the radius to. I don't measure it out here. And we can draw what happens to all of these rays. Here again, a ray going to a point like this is going to reflect. This radius line is perpendicular, and so it's going to come back off at a similar angle from the normal, which is what the radius is. And it's going to cross at a point right at the focal point. So a concave mirror does the same thing as a lens. It takes parallel rays coming in, and it makes them all cross at a focal point. I could draw some more rays in here. I think I won't. But they would all cross at this focal point. And so the mirror also has what we would call a focal length. We could put that in right here and call that the focal length F, just like we do for a lens. The only difference is that in this case, these rays are on the same side. So the picture that we had with the lens with the rays coming over here sort of been folded back over, and we see it on this side of the lens. But the very same formulas apply. All the formulas are essentially identical for mirrors. So we'd say 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. And then the one additional thing I'll say, you might have been wondering about the relationship between the center of curvature and the focal point, or the focal length and the radius, and it's just 2 to 1. So we can write this as 1 over the focal length or 2 over the radius, and that sort of captures everything that way. So we can now consider a case where a mirror has some object out in front of it, out here somewhere, and the rays, we could draw a focal point here and a center out here. The rays would do something like so, and a ray that goes through that one comes out parallel, and a ray that goes through the center here would hit the mirror and come right back. So we're going to get an image somewhere about there. And once again, this is the picture where all of these distances are positive. So here would be the object distance out to my object out here. It's forming an image right here. So that distance is the image distance. And here is the focal length of the mirror right there. And these are all positive numbers using this same formula that we've done before. You can, of course, have negative numbers. You can form an image that's behind the mirror. That's what happens, for instance, when you just walk up to an ordinary mirror. The image that you see of yourself is behind the mirror somewhere. And in that case, the image distance is negative. Let's do a case like that. So here we're going to have, I'm just going to work an example now. Let's say we've got a mirror that's got a rather gentle curvature. It's got a long focal length, like so. This is going to be like a cosmetics mirror. And now let's give this a radius out here is going to be 90 centimeters. So R is 90 centimeters all the way out there. So that puts the focal point here at 45 centimeters. And now let's imagine somebody sticks their face real close. And so here is our face. and we're in at just 20 centimeters, trying to look at ourselves and see where is the image that we see. We have all the usual questions. What's the focal length of the mirror? Well, we already calculated the focal length of the mirror, but where is the image, and what is the magnification, and what kind of image are we going to see? So we've already calculated the focal length for this mirror. We got that just by saying 1 over f is 2 over r, and so the focal length is just 1/2 the radius, or 90 divided by 2 is 45. So I've done that just for completeness. Now let's go on and try to work out where the image will form. That's using this usual formula, 1 over s object plus 1 over s image equals 1 over the focal length. So what are the numbers in this case? Well, the object is here at 20 centimeters, and that's on the usual side of the mirror. Just like this example up here, the object is out in front of it somewhere. So that's a positive number. The image is what we're trying to find, so we'll just leave that. And then the focal length of the mirror is this 45 that we've calculated, and that's also positive. A concave mirror like this has a positive focal length. Okay. And I'm going to leave these both in centimeters, and we'll get our answer in centimeters. To do that calculation, you should find that the image distance is minus 36. Go ahead and work the example. You'll take 1/45 minus 1/20. That gives you a negative number, and then you have to invert it. So you're going to get minus 36 centimeters. What on earth does that mean? Well, remember, this picture is where everything is positive. So that's where an image forms on this side of the mirror. And so in this case, the image apparently forms behind the mirror at 36 centimeters. So if that's 20, we've got an image back here somewhere. How big is it? What's going to be the size of our image? We can calculate the magnification now. Remember, magnification has this minus sign in the formula, SI over SO. So that's minus, and then there's a negative 36 for the image distance. You have to keep track of the signs carefully here. Dividing by 20, we get now a positive 1.8. These two minus signs cancel, and you end up with positive 1.8. Positive means it's right side up. This is not inverted. So our image is going to be back here, and it's going to be larger by a factor of 1.8, almost twice as large as the object. And it's going to be 36 centimeters behind. It's going to be that much larger. So what sort of an image is this? Well, it's upright. It's not inverted because of this plus sign. It is a virtual image. It is formed from rays that seem to be coming from there. Let's draw an example. A ray from the eye here, if it was going parallel, it would end up going through this focal point. And you could draw a ray down here that hits the vertex, and it would reflect off kind of like so, be spreading out even further. We can draw another ray sort of like so, and these all would seem to be coming from a place back here where the eye of our virtual person is. I need to move the eyes to get this right. Now, those rays don't really go through that. The rays forming this are these real rays over here, but they seem to be coming from this point back here. So that's a virtual image. You put a piece of paper there, nothing shows on the piece of paper. The rays forming that are out here. They don't get to the paper. So that's a virtual image. So it would be upright and virtual, and it would be enlarged. it would be almost twice as large as the original. If you want to get the exact number, you have to say, well, how big is the object? Say your face is 25 centimeters tall, then you'd take 25 times 1.8, and you'd get 45 centimeter tall for the image over here. If you wanted just to work an example.